So the next talk is by Simon Kramer, Logic of Non-Monotonic Interactive Proofs.
Thank you for attending my talk. Thank you. So this is, I'll speak about a variant logic of some existing logic. And so I wrote this up, I finalized it here at this institute, and I'm very grateful for this because it was a very peaceful and nice time. And so thank you very much. So the purpose of this talk is to explore the modal difference between monotonicity and non-monotonicity in the case of what I call interactive proofs. And some of you might heard of this concept, which was originally defined in cryptography. And there it had a strongly resource-bounded flavor. So in the context of probabilistic polynomial time computation. I'm not yet in this context, but that will be further work. So by an interactive proof, intuitively, I understand the following thing. So the idea is that if my peer reviewer knew my proof, then she would at least then, in that instant, know that its proof goal is true. So that's the intuition of what I call an interactive proof. So in some sense, with an interactive proof, we want to communicate fact knowledge, the fact being expressed by the proof goal. And so the difference between monotonicity and non-monotonicity is in the red part, right? With a monotonic proof would convince you always, right? In the instant you receive it, and henceforth. And for a non-monotonic proof, this is not necessarily the case. So we have these two aspects, right? Monotonicity and non-monotonicity. And so, as I try to suggest in this informal definition of interactive proof, we induce the knowledge of the proof goal with the proofreader. And because we induce knowledge with the proof, we achieve an epistemic impact. That's what I mean by the first line of the table there, right? We achieve an epistemic impact. In the case of monotonic proof, the impact is durable. Thank you very much. In the case of monotonic proof, the impact is durable. In the case of non-monotonic proof, the impact is fragile because it could possibly sort of cease to be the case, right? And so the knowledge of the proof goal with monotonic proof is persistent, right? Whereas in the non-monotonic case, it is ephemeral. And so the knowledge transfer that happens when we communicate a proof, right? Because the proof is about inducing the knowledge of its proof goal with the proof reviewer. So in this sense, there is knowledge transfer. So the knowledge transfer in monotonic proof is lasting, right? Whereas with non-monotonic proofs, it is temporary. So this is sort of a philosophical prelude to my talk. Sorry?
Would you please
Yep.
restate what you mean by monotonic and non-monotonic proofs?
Restate it.
Yeah.
Repeat.
Yeah, repeat.
I see.
Because we missed the point.
You missed the point.
Because that is the fundamental thing.
Yeah, it is very important to this difference, of course. So this slide is just sort of a philosophical prelude. Are you missing formal details or sort of more intuitive philosophical elucidations? I can give you the formal details later on, but not on this slide.
Then the definition. Tell me the definition. What do you mean by monotonic proof? What do you mean by non-monotonic?
Well, as I tried to suggest, if I send you a proof, a monotonic proof, then that proof will convince you, so when you receive it, right? That proof will convince you that the proof goal is true in the instant you receive it and henceforth, right? A non-monotonic proof if I send you that proof, if you receive it, will convince you in the instant you receive it, but not necessarily henceforth. Right? So in the context of distributed systems, for example, I mean computer systems in general, we have facts that are true at a certain state, but not necessarily in another future state, for example, right? So, I mean, in general, in modal logic, right, truth is evaluated with respect to points, pointed models. So, and in a computer science setting, a point corresponds to a state, right? A state of the system. And so there are typically properties that are true at a certain point, so in a certain state of the system, but not necessarily in all other points, right? So actually, in the case of computer systems, non-monotonic proof, that's sort of my point, seem to be much more relevant than monotonic proofs. Of course, if you say to a mathematician, listen, I have a non-monotonic proof that this is true, then he will say, well, I mean, you're joking. I mean, you know, whenever a mathematician proves something within a certain theory, formal theory, right, then once he has proven it, it is true, right? And it remains true, so to say, at least as long as you work in a formal system whose consistency is known. Otherwise, I mean, you cannot really say, right? Okay, so it's, of course, if I send you a mathematical proof, then sort of you did not know it before, right? And you might not have known that the proof call is true before, so if you receive it, then you know that the proof call is true. So mathematical proofs are sort of typically persistent proofs. Is that okay for the moment? Okay. So here, we look at agents as proof checkers. So the person, the peer reviewer who receives the proof is the proof checker. And they also act as signature checkers, as we will see. And I would like also to mention this keyword, constructive Kripke semantics. So I will give you a standard Kripke semantics, but whose accessibility relation I will define constructively. So I will construct it from more primitive things. I will not just say this is an equivalence relation. I will construct this relation. In this sense, it is constructive. So it's not intuitionistically constructive, but I construct it from more primitive things. And we are in the context of multi-agent distributed systems. And so Oracle computation also plays a role here, because we imagine, right, if my peer reviewer knew my proof, so we imagine, right, then she would know that the proof call is true. So in some sense, I act as an oracle for my peer reviewer, right? And I understand proofs as sufficient evidence, right? So if you receive enough pieces of evidence, they will constitute a proof to you. They will induce knowledge. So I have just two pictures what this is about. In some sense, it's an Indo-European homage to Japanese aesthetics, because in India, as far as I have understood, it's about eternity, it's about infinity. Ramanujan, the number theorist, not the logician, was also called the man who knew infinity, because his work was about infinite series and sort of approximating the number pi, amongst others. Now, Japanese aesthetics it's really about the ephemeral, the beauty of the ephemeral, and we have the cherry blossom, of course, that symbolizes this this sense of beauty. So this is about Japanese beauty in some sense. I hope it's not too ugly what I present. So. Okay, so there is, I would like to recall sort of the definition of non-monotonicity by Mackinson. So this is from a chapter in the Handbook of Philosophical Logic. And so I rephrase it model theoretically, right, because he states it proof theoretically, because non-monotonicity usually is treated in a proof theoretic way. So he says the proof, so I rephrase it, right, in my context. I say, because it's a modal language also, right? The proof modality of my logic, which I call LIIP, logic of instant interactive proofs. So it internalizes a non-monotonic notion of proof in the sense that it can happen that a proposition phi can be proved with a non-monotonic proof M to an agent A, and so if A knew M, then she would know that phi is true, okay, so proving in this sense. In some system state S, so that's why I say model theoretically, but not anymore in some subsequent state S prime in which A will have learned additional or lost previously learned data M prime. So the addition of more data might lead the proof that I received before to cease be a proof, right? And if I lose data which I had previously had and contributed to the understanding of my proof, so to say, right, will also lead to that proof. M, well, I mean, it will not be a proof anymore. So and of course, in distributed systems, this happens all the time. We receive all the time new data, right? And we might also lose data. So non-monotonicity is really a big issue in distributed systems. So this is about the possibility to internalize proofs of ephemeral facts. And in computer science, except maybe for invariance, right? When we talk about invariance, and invariance, of course, is a persistent fact, right? But except when we talk about invariance, almost everything seems to be ephemeral. Think, for example, about cryptography, right? If you encrypt a certain message and you want to keep it secret, by encrypting it, you want to keep it secret from certain people, then this secrecy is ephemeral because it is sufficient to sort of publish the key, encryption key, right? Or I mean the decryption key. And then the secret is destroyed. So especially cryptography is full of ephemeral facts. And just recall that a proof intuitively must not prove false facts, false statements, sorry. And the proof must prove true statements, right? So if the proof goal becomes false after you receive the proof cannot be persistent, cannot be monotonic, right? Because proofs must only prove true statements. Whereas in the meanwhile, if in the meanwhile the fact has become false, right, the proof cannot be a proof anymore. So I'd like to recall some formulas. So this is about inducing knowledge, and I mean inducing knowledge in the sense of S5 modal logic. So this is very standard notion of knowledge. So we have an operator, agent A knows that phi is true, right? And we have a certain system state and a certain model, right? So this is the frame, and this is a valuation. And we have a set of system states. So this small s is an element of this capital S. And we have an indistinguishability relation, right? And then the semantics of this is defined in this standard way. So this says, in all states S prime that are indistinguishable from the current one state S, right, phi must be true. In that case, agent A knows that phi is true by definition. And so this is an indistinguishability relation, which means it's an equivalence relation, right? All what we need to define knowledge is an equivalence relation. And so because it is an equivalence relation, we get the following laws, right? I mean, of course, we get the Kripke law in any case, right? But because this is an equivalence relation and thus reflexive, we get the truth law. And then because it's transitive, we get this positive introspection law. And for the rest, we get negative introspection also. And then, of course, also because it's a standard modal logic, I mean a normal modal logic, we not only get the Kripke law, but also the necessitation rule. Okay, standard S5 knowledge. So just to recall that. I need that because this is what I induce. This is what I mean to know a proof goal. Knowledge in that sense. Yes?
That's a problem with it.
Yep. Sorry? The previous line. Previous one. No. Proofs must not prove false statements. Proof must prove true statements.
Proofs or proof techniques?
Sorry?
Do you actually mean proofs or proof techniques?
No, proofs. Proofs.
Because then proof by contradiction, right? Does it go against it?
No, because what if you want to prove not phi, for example, or what? Well, not phi is also, you want to prove that not phi is true, right? So phi is false.
Yeah, but then
What?
you come up with an explicit contradiction, which actually says that the negative is false, which means that the original one is true.
Well, but then you're in a different context, right? So when you make a proof by contradiction, then you you make a hypothesis, so you extend the context, the proof context with a hypothesis, right? I mean, I'm talking about the proof goal. Okay? Sorry. I should have said proof goal, right, instead of statement. Yeah, thank you. So, more of the formal stuff. What's going on? I don't know what is happening here. Okay. So I talk about proofs. So I need a term language because proofs in this context are terms. And we have agents because these agents communicate with each other and send each other proofs, right? So I have a set of agents. Agents A. Yes?
By proof, do you mean passive proof or do you mean the mathematical proof?
If I mean?
By the word proof,
Yes.
do you mean the proof arrived until that moment or the mathematical proof of a fact?
So proof here, for me, is a thing that if you knew it, it would make you know its proof goal. So I don't care about exactly mathematical proofs. Of course, if I have written up a mathematical proof of a theorem, and you are my peer reviewer, I send you the proof, right? Then this mathematical proof must also have this property in order to constitute a proof in my sense, so to say, right? So in this case, I'm talking more about social proofs, right? Mathematical proofs in the sense of social proofs. But I mean, they're not less formal here. I mean, it's a completely formal setting. But I don't restrict myself to proofs that have been written down in a formal proof system, right? The only thing it's a declarative notion of proof. The only thing I care about is that they induce the knowledge of their proof goal. That's what I care. And of course, the mathematical proof that I send you for peer review should also have this effect. Should convince you, right? Should convince you that the proof goal is true. So I have some set messages which are actually proofs, because any message proves something, and any proof can be a message, right? Any proof, I can send any proof, so it's clearly can be a message, and any message proves something. Because if you knew it, then you would know that you know it. I mean, the proof, right? So it at least proves its own knowledge, its own sort of individual knowledge, right? So this is why I identify proofs and messages. It's the same thing here in this context. So let's take a typical message, M. So it can be an agent name, right? We refer to agents by their names. So and names can be transmitted, so they are examples of messages and proofs. Then you can have any kind of, application-specific syntax data that you like. I don't care. I leave it blank. This is why I call it B here. But what I need is a notion of signing. So that a message, this means that a message is signed by agent A. So for example, if you're in the context of public key cryptography, then you would see here the private key of the agent A. I don't care how you do this, how you implement this signing. I only care that this is signed by agent A. So for example, tomorrow you will see me again in this conference, and you will see me, right? So my appearance is my signature in this context. The way I smell, the way I talk, right? This is my signature. So it allows you to identify me. And then I need pairing, right? So I pair together two messages because I need to put together, you know, the data, right? And then of course I can also project, so I can focus on some part of the pair, right? Then of course I have, so this is the term language, right? Now comes the formula language, the language in which I make the statements, the sentences. I can write down the sentences. I have an atomic proposition, right? So the set of atomic propositions, calligraphic P, is not completely arbitrary. There is this kind of proposition, right? So I have agent A knows message M. So because I have to be able to express what I mean by knowing the proof, right? So we have proof or message knowledge, that's one kind of knowledge, and I use the small k for it, right? Agent A knows the message. The message does not have a truth value, right? It's a sentence that has a truth value. So this is message knowledge. It's a very syntactic form of knowledge. Okay, then just to recall the syntax of the existing logic. Well, I have these atomic propositions, then a negation, conjunction, and here this modality. So it's a unary modality. It has a single operand, right? Phi is the operand, but it has three parameters. So namely the proof term M, an agent A, and some community of agents calligraphic C. And this is pronounced in the following way. This means that message M can prove, so we talk about potential proofs, right? I will explain what I mean by that. Message M can prove that phi is true to agent A, and this fact, right, that M has this proof power to agent A, that fact is persistent common knowledge in the community calligraphic C plus agent A. Okay? Because usually what is accepted as a proof depends on the community in which you are in. Right? So this is why I bring in the context, the calligraphic C. This is the existing logic. The logic I'm talking about in this talk has almost the same syntax. I mean, it's isomorphic, but it has this, I use this, this operator here, right? The difference to the previous one is that is the following. This reads that M can prove that phi is true to agent A, right? And this fact, so this proof power, is not common knowledge and it's not persistent. It's common belief. This fact is common belief in the community calligraphic C plus A. We cannot have common knowledge. We cannot have persistent common knowledge. It's about this non-monotonicity, right? Yes? Okay. So, okay, well, you asked a lot of questions. So we have for the existing logic, we have the axioms of classical propositional logic. Then I have the axiom agent A knows A. So all agents know their own name, string, so to say. That's what it means. Say, if agent A knows the message M, then she can sign it, right? She knows that message signed by herself. If she knows a message signed by B, she can also know M and the name of the signer, B, right? If she knows M and another message, M prime, she knows the pair of it. And of course, the other way around. So these are like this Dolev-Yao style rules, right, of Dolev-Yao cryptography. And this is also why it is non-resource bounded, right? If you wanted resource bound, you would not allow arbitrary synthesis, right? You would not allow this direction, right? You would only allow that direction and some controlled version of this direction. But this is then the whole problem of finding a resource bounded version of this logic to control this direction of the implications. Then you have this. So this is the Kripke law, right? So if M can prove this implication to A, then if M can prove the antecedent to A, then it can also prove the consequent. And I have the Kripke law here because this is about potential proofs or sufficient evidence, right? If M is sufficient evidence for this, and M is sufficient evidence for this, then it is also sufficient evidence for this, right? If you're in a non-resource bounded setting. Then I have this. This is a restricted form of the truth law, right? If M can prove phi to A, this is the potentiality, right? This is why these proofs are potential. If M can prove phi to A, then if A actually knows M, phi is true. And this is why this is interactive. So if, or this is sort of community-based, right? If M can prove phi to agent A, then if A signs M, this is a proof to any agent B in the community, right? In the community, including A, that A knows M and that M can prove phi to A. Then you have this one. So if M can prove phi to A, and this is common knowledge in the community C, union C prime, then of course it's also common knowledge, sorry, not common knowledge. Well, no, it's common knowledge in that logic, in the smaller community, right? This is an important axiom. This characterizes almost the monotonicity, right? So this is a rule, right? These have been axioms. This is a rule. So whenever A knowing M implies that A knows M prime, then if M prime can prove phi to A, then also M can prove phi to A. Then we have modus ponens and necessitation. And here we have necessitation because I care about local truths, right? So phi is a validity, is a theorem, so to say. So it's true in any point of any model, right? And I don't care about these truths. You could, of course, if you liked, but this is not my emphasis. I care about ephemeral truths or local truths, right? So I don't care. Anything can prove a tautology, right? Tautologies are trivialities in this context. Now, here is the difference between then the existing logic and this non-monotonic variant, right? So the logic itself is monotonic, but the internalized notion of proof is non-monotonic. So the difference is here, see? Before we had an implication, right, from here to here, and now we only have an equivalence, and here also. But the surprising thing, at least to me, was this axiom. This is not an axiom that I invented or sort of guessed, but actually I found it by sort of from the semantics that was derived from the existing logic semantics. And I would like to point to you, if you give me a bit more time, I would like to tell you how I found this rule. So the difference is, you see, this sort of quantification, right, is here at the outermost level, and I need to give here a bit more information. So M is not enough. I need to assume that M plus the name of B, this guy here, right, can prove that phi to agent A. Then everything is the same as before. I need to give a bit more information, namely the name. And so people who have been working in cryptographic protocols know that names are a big issue there. I suspect that this is because of this axiom, actually. Or maybe this axiom can explain some of this difficulty. You can derive then a couple of laws. So with respect to pairing, we have an idempotent commutative monoid, right? You can derive these laws. We also have some neutral elements. You can also derive this property, which is sort of a one-way combinator property, right? You can project. And you can also derive this S-combinator property, right? And so in some sense, our agents act a bit like combinators, right? But I would like to stress that the other direction, right? So this direction here, right, does not hold. This would mean that agents could guess, right? If from A knowing M, she would automatically know M and any message M prime, this would mean that she could guess anything. This is extremely non-resource bounded. I don't want this. Of course, this is totally unrealistic. In a context of probabilistic polynomial time computation, of course, you want to allow a certain amount of this, right, of this direction. Because agents can flip bitcoins, right? So, you can derive these laws, but I don't have the time to comment on this. Just this law that you had in the monotonic version, you don't have anymore, right, in this non-monotonic version. And all the gray shaded logical laws, you don't have either, right? So this is a very important law. You don't have it anymore, right, in this non-monotonic logic. This you have, this you don't, right? So you cannot accumulate information anymore, you see? If m proves phi and m prime proves phi prime, then it's not necessarily true that m plus m prime proves a conjunction. Because adding proof terms, right, is sort of makes our context richer, and precisely non-monotonicity is about sort of being in the same context and not sort of making it larger or shrinking it. And this is then the constructive accessibility. The reason why we have this B, the name of B, right, in the signing rule is because of that. So this is the difference. It's not reflexive anymore, and we have this message M. But besides that, it is standard Kripke semantics. You see, this modality has this semantics, and you can unroll it so that this becomes equivalent to this. So you see, I say I quantify over all worlds that are just a bit richer, right, than the current one. Namely, you just add the message M. You add the message M to the current state, and that's it. And in all those worlds, we must have this implication. If A knows M, then she knows that phi is true. So the difference between non-monotonicity and monotonicity is that with monotonicity, you would have here reflexivity, and not just S tilde enriched by M, but any S tilde richer than the current state. So this is the difference between monotonicity and non-monotonicity. Then you have the accessibility property, and you can prove a soundness and completeness result, and I should shut up, I guess. Thank you.
Yeah. So, sorry for running a bit late.
Yeah, I'm sorry. Yes.
He'll be talking on non-interference for intuition necessity. Thanks.
So this is joint work with my colleagues, Karin Pritchard and James Riley. The basic context of the talk is something which is quite familiar for all of us. So it's in the context of the necessity modality of S4. We have the standard Hilbert axioms there, right? And in particular, what I'm going to be doing is I'm going to be inside a intuitionist version of this calculus, and I'm going to be interested in not only in the formulas but also in the proofs of these calculus. And the intuitionist version, Fennig develops a natural reduction system, so basically a lambda calculus, and Bierman and De Paiva show us a sequence system, right? And I think what's useful perhaps for some of us to keep at the back of our mind is that there is a nice categorical semantics of the formulas and the proofs. So we want to think of, or we could think of box as a comonad. From that perspective, distribution is functoriality, reflexivity is the co-unit, and transitivity is the co-multiplication, right? So that's the general context. In particular, what I'm going to be looking at is sort of indexed version of this calculus, right? So my indices are going to be picked up from some preorder. I'm going to give you some examples in a minute. And the idea is that for each element of the preorder, I have an associated box modality. So for example, for A, I have box A, which satisfies the box axioms. Okay? And we want some sort of coherence across different elements of the preorder. So what I want is that if B is less than A, then I want that implication to hold. Again, from a categorical perspective, what you want to think about is basically that there's a natural transformation between the functor for B and the functor for A. Okay? So that's one way to think about it. And what do I really, and of course, there could be other commutation laws, and for the reasons which will become clearer as I go along, I'm going to hand wave my way about these commutation laws. Okay. So now, let's think of one non-interference, a very first attempt, very crude. Okay. So what's the idea here? What I want to make sure is that there is no information flow, if you will permit me a word from security and from programming languages, between differently indexed modalities. Okay? So one approximation, let's think of a crude approximation. Let's say I'm deriving a formula box A alpha. And I'm deriving this from a bunch of hypotheses, and well, let's assume that this set of hypotheses is deductively closed, right? So then what non-interference means is that I must be able to perform this deduction solely from those hypotheses which are in the scope of a box A. Okay, so everything else is irrelevant, right? So what are the consequences of such a thing? So for example, if B is not less than A, then I don't want to be able to deduce box AP from box BP. There's no information flow there, okay? And similarly, I can't do the distribution in the relevant cases. Okay, so this is the general kind of theorem that I want to look at. And what I want to do in the rest of my talk is the following. I'm going to sketch for you the use of this logic already in a couple of applications in computer science. I'm going to argue that non-interference, in the sense I'm talking about the no information flow between principles, is a fundamental meta-theoretic property necessary for this logic to be used in these applications. And the main technical meat of my talk is I'm going to show non-interference for such a system. Okay, and as we look at these applications, we realize that there isn't really perhaps a canonical version of this logic that gets used as is in these applications. So what I'm going to try to do is going to try to make my non-interference proof as general as possible. Okay, in particular, what's going to happen is that the result I show is going to hold for any system with fewer proofs. Okay, so we'll see how we get there, right? So this is what I'm going to do in the rest of the talk. I'm going to start with a couple of examples and spend some time on the logic, and time permitting, I'll tell you as much of the proof of the non-interference theorem as I can get. Okay. All right, so let's start with the examples. My first example is about the use of the necessity modality in writing security policies. Okay, so what's going to be the lattice here? The lattice, in this case, the preorder is going to be a lattice, and the lattice is going to be what the security people call principles. But what is a principle? It could be a process, it could be a person, it could be a location. And what does the ordering mean in this context? What the ordering means is that if B is less than A, then B is a less secure principle than A. Okay? And what are these policies going to be? I'm going to give you examples in a minute. These policies are basically going to be, they're going to specify the capabilities, the permissions that are available to principles. Okay? So let's look at some examples. Okay? The basic propositions in such a policy is about the atomic formulas, if you will, the O's, are object references. Okay? So a capability to access an object. That's what it's going to be. And the way I want to read box A O is that A is permitted to possess this capability. That's how I'm going to read it. Okay? And there are really simple examples of these things. Okay? So let's look at something like O implies O prime, where O and O prime are both object references. These, from a programming perspective, where these are guarded objects. Okay? So what's a guarded object? Well, let's say I have one O implies O prime. In order to get to O prime, I need O. Okay? So if you want to think of it this way, you can think of it as a ciphertext, where O prime is the plain text which has been encrypted with the key O. Right? And when I put a box B around it that says that B is permitted to have access to this ciphertext. Right? And the principles of the more underlying model logic are really nice. For example, what I would like in this case is to say, if B has access to the ciphertext and B has the key which encrypts it, which is O, then B also gets access to the plain text below. And the underlying logical principle gives this to me, right? What is rights for principles can be forgotten during the deduction process, but as I want in such a setting, I don't want to be able to manufacture it. So I don't want of course, I don't want the implication going the other way in the co-units there, okay? And the principal naturality in this example has the natural interpretation that if you have a more secure principle, then they have access to more secrets, basically, okay? So that's why the logic works here. And in this setting, in the use both in the paper I showed you and in the use in my own work, commutativity happens naturally, okay? So for what I mean by commutativity is just that box A and box B commute, okay? So now, what is non-interference here? In this setting, what non-interference tells me is that the logical deduction does not transfer capabilities between the principles, right? So, for example, the first thing about there is a non-theorem that says, well, just because B has access to a reference O, that doesn't mean that A has access to the reference, okay? And similarly, we want to say that, okay, suppose A has a piece of ciphertext, B has the key for the ciphertext to decrypt it, but still A will not be able to decrypt it, right? So non-interference says that the logical deduction does not permit these things to happen. So, okay? And this is necessary for the way these policies are used in a distributed system. So let's imagine A, B, and C lying around. These are principles. At each of these locations, A, B, and C are locations. At each of these locations, there is a program there, sitting there, making sure that accesses are happening in an appropriate way, as permitted. And what non-interference ensures that the reasoning at these different locations are independent. Okay, so this is necessary for us to be able to effectively use in a distributed system. Okay, so that's our example number one. That's security. Okay, our second example is a sort of a little bit more. You have to bear with me for a bit of notation. It's a little bit more internal to the theory of programming languages. So what I'm going to do is I'm going to show you how these indexed logics are already used to write type systems for modeling exceptions, okay? So in this case, my preorder is going to be sets of exceptions. My ordering is going to be B less than A if B is a subset of A, okay? And what's the interpretation here, okay? So if you will permit me some programming language jargon, right? So I have an expression E. I'm going to give it, when can I give it a type box A alpha, okay? So let's say alpha is a normal type int, okay? So box-free type. So what do I want to say? Well, E, when I run E, I run the program, I evaluate E. If it terminates normally, I must get a value which is of type alpha. But on the other hand, what may happen is when I run E, there may be some abnormal situations called exceptions, right? And E will have the type which is written up there. If any abnormal evaluation, any exception which is raised then is contained in the set A, okay? So that's what the types mean in this system. And in this context, all types are in a box context, okay? So for example, pure functional programs, if you will, are given that type because they are not going to raise exceptions, okay? So in this system, in fact, axiom T won't play a role. In that sense, it's an impoverished system. And principal naturality, what it captures is it captures a natural conservativity idea, which is that if you have a program which only raises exceptions which are in the set B, and B is a subset of A, then of course we can give it a more conservative type, box A alpha. Okay, so there's a natural interpretation for that. And the other modal axioms ensure that typing is enough. Typing works normally. If I have a function, alpha or beta, and it can only raise exceptions when you're evaluating the function, you only end up with exceptions in A. The argument can only give you only exceptions in A. Then of course I can run the function with the argument, never going outside the bound given by the set A. Okay, so this is why the normal typing rules which you would see work naturally. okay? And, one can type, you don't need to read the slide, just to say that one can type the usual exception combinators, both to raise and to handle in the ways you would expect it to, okay? Now here, what does non-interference mean in this example, okay? So here what we're going to do is, it's really useful to take proofs as programs view, okay? So instead of thinking of proofs, I want to think of them as functional programs. And the basic content of non-interference is that no pure logical term can raise exceptions, okay? That's the basic content. So for example, the fact that the first formula there is a non-theorem says no pure term can handle the exceptions which are in B minus A. And in general, the way one should think of non-interference is when you're evaluating a functional program whose type is box A alpha. Now, what are the computations that this functional program can use as subcomputations? What non-interference tells us is, in fact, it cannot ever touch any computation if the exceptions that it raises are not included already in my type, okay? This is the reason why one can use this logic in our typing system, as a static typing system, okay? So non-interference is important here from that perspective, okay? So that's our setting. Now, hopefully you have some idea that this is a useful thing to have. And so now what I want to do is I want to work through a sketch of the logic and a sketch of the proof. This is what I'm going to do. All right, so let's start with the logic, right? A design comment, right? We can't have too many proofs in the logic, clearly, because then we're going to lose non-interference, okay? On the other hand, we want as many proofs as possible, just for the reasons I've said, because because we have there's no canonical use of this logic, so we want to build a world which is as large as possible, right? And just also because the particular way I'm going to try to prove non-interference, which is basically what I'm going to do, is I'm going to build a proof-preserving translation of the formulas of my logic into intuitionist propositional logic, okay? And so, it would be nice for me to make this translation work for as many proofs as possible so that I can reuse it as much as possible, right? So these are the constraints, okay? So I want you to keep this in your back of your mind, because if you don't like some of the particular rules I use, you're welcome to drop them. You're not losing the theorem. That's the point I'm trying to make, okay? So, what I'm going to show you is sequent calculus, like one we saw in an earlier talk today. And it satisfies the usual properties. I mean, I can restrict my axiom down to atoms. I'm not going to use admissibility of cut. This would follow standard presentations. Weakening is admissible. Again, I'm not going to use it, but it's useful to keep in our mind, okay? So this is going to be my, it's a propositional logic. With just functions, with just the function space, that is implication and the conjunction and the modality, okay? I will come, towards the end of the talk, I'll comment about, a little bit about, enriching the formulas permitted, okay? And the rest is quite standard. I mean, we have our identity group, which looks, axiom and cut as usual. We have our structural rules for intuitionist logic. We have the introduction rules on the left and the right for conjunction and the unit. And we have the left and the right rules for implication. Totally standard stuff, okay? Nothing unusual going on there. Now let's move to the modality, okay? So first the rule on the left, okay? Which corresponds to the co-unit of the comonad, right? And that is standard. This is again what we saw in an earlier talk today. So it's familiar, okay? So all the ad hocness, if you will, is going to be in the rule which introduces box on the right. And the way I've written there is going to be the way the way my logic is going to keep it. So basically, I'm allowed to introduce box on the right if the sequent on the left is something A available, okay? The A being the same A which is indexing the box, okay? And what is the intuitive idea? Whenever you see A available, I want you to think of formula alpha is A available if it implies its boxed A version, okay? That's the idea. And a sequent is A available if all the individual formulas in it are A available, okay? So here is what we would do. Okay, let's write different versions of this just to get a sense for it. The first version is the standard one, which is we say formula beta is A available if it has a box A at the outermost. Okay, and with that definition of A available, the rule which introduces box on the right looks standard. Basically, if the context is completely boxed, I get to introduce a box on the right. Okay, that's our first cut. This is what we want to do. And if we just had that, then we have some normal-looking theorems. So, for example, we have co-multiplication on the right is derivable, functoriality is derivable. Okay, this looks very standard, right? But we have to go a little bit further. Okay. Because we want to make sure that we get principal naturality, okay? So what do? We loosen, we're going to be loosening. The first thing we'll say is, oh, beta is A available if it's of the form box B gamma, okay, where provided B is less than A. So there's a mild weakening here, right? A is less than A, so this includes the version we have written before. And the reason to do it this way is to permit the derivation of principal naturality, like there. So basically, how do you derive this? You start off with box B alpha deriving alpha, and box B alpha is A available, so I can use the promote rule to put a box A on the right. So the point of weakening is to allow principal naturality, okay? Maybe that's not as controversial, okay? Now I'm going to permit more formulas, okay, to satisfy the thing we have there, right? So the thing I'm going to introduce is something here, which I said box B alpha is A available if the alpha is A available, okay? So this is really a genuine commutativity principle. That's what it is. In particular, what we see, I mean, the simplest thing we see there is that box A, box B alpha is B available, right? So from this, the details don't matter, but I can derive the commutativity. Okay, so it's loosening stuff more. All right, and as a last weakening, what I'm going to do is I'm going to really take a proofs as programs view of the function space. So basically, I say, okay, I look at the function space, the implication beta implies alpha, and then I say, well, in a program, the only way I'm going to use it is by applying it to an argument. Okay, in which case the only use I'm going to make of a function is from its result. So I say, well, so beta implies alpha is A available if alpha is A available. Okay, now this is a really unusual thing to say from a modal logic perspective, and I'm doing it for the reasons I've described. It's not necessary, but it's to make my theorem more general. In particular, a formula like this is A available, alpha implies box A beta, and in particular, what we see is now, that means that my logic is allowing you to prove that funny theorem there, okay, which is that I can derive the boxed version of alpha implies box A beta. Okay, so this is the sort of the logic. So it's basically traditional principal index logic, but with just a few extra theorems. All right, so now just I'm going to give you a sketch of how my non-interference is going to work. Okay, so what's the proof technique? So what it is basically I'm going to describe for you a translation of formulas from the logic I've just shown into intuitionist propositional logic. So all the modalities will go away. Okay, this translation is going to do some interesting things. But the most important thing to notice about it is that it is designed not only to preserve provability of formulas, but to actually preserve the proofs. It's going to do something very uniform on the proofs which I start off with. And this technique was pioneered by Martin Abadi when he was studying non-interference properties for a modal logic, but with a lax modality. Okay, so while this technique is sort of pioneered there, we had to invent some new things in order to make things work for us, because unfortunately, the monads, which is the lax modality of Martin, and the necessity modality, they're not duals. For example, both of them distribute over conjunction. Okay, so even though the proof structure is the same, there is some machinery that is specific to our setting. Yeah? So the first piece of this machinery is going through very simple study of normal forms. So we have distributivity properties for conjunction, right? So what we do is we basically split up formulas into what I call unique result formulas and multiple result formulas. So basically a unique result formula is something which looks like the shape which I've drawn there. All that it means is I don't have a conjunction if I go down the right spine of an implication. That's all. Okay, it's nothing else. And multiple result formula is just a conjunction of unique result formulas. Again, this is not, this doesn't restrict the provability of formulas. In fact, it also does not restrict the proofs, which means that basically I can take a proof in the system I showed you and restrict it down just purely to these these formulas in this special syntactic category, and I still maintain all the proofs. Okay, so simple proof theory. Okay, and now this is my main theorem. What I'm going to show is I'm going to show you two translations in the next few minutes. I'm going to show you two translations which preserve provability. Okay, this is important. Okay, and the target of these translations are not going to have any modalities whatsoever. And the way I want you to think about these translations is as a combination of two of them. Okay, so the one with the angled brackets is the one I'm going for. I'm going to split it into two parts. First, what I'm going to do is I'm going to remove all the principles except one. Okay, so this first bit is the subtle bit. I will explain that in a minute. The second bit is a totally standard translation from modal to propositional logic. Just drop the modality, because the result of doing the first translation is a formula with modalities indexed by only one principle. So effectively, it is it's standard intuitionist modal logic. So what does it do? So here in the first bit, what the first translation, what it's trying to do is it's going to enforce the non-interference property. Okay, that's basically what it's going to do. So that's the bit I'm going to show you. Okay, so let's walk through it. Just to get some feel for it. Yeah, so let's think of this plus version of that translation. All that I'm doing is I want to remove all the modalities which are different from A. So of course it's going to just work as you expect there. True, now there's no change. Propositions, there's no modality. I don't change. Conjunction, I do it compositionally. But now let's come to implication. Okay, and all that I want you to look at here is the top line of the implication, right? So I have alpha implies beta, and beta is A available. Okay, so now I have a problem. I have a problem because I want non-interference, right? So what I want to do is I want to go into alpha. I'm going to show you. I want to go into alpha and remove anything which is not A available. Okay, that's what the translation is going to do. So intuitively, if you look at the top line, that's why I shift to a related but different translation, which is the one with the minus superscript, which is only going to produce A available formulas. Okay, all right, and so now I'm just describing for you the key of the minus portion of the translation. And there you see the only thing for you to notice is, which gives you a flavor of what it does, is what it does to propositions. A proposition is not A available. So of course I have to kind of zero it out. And in this context, what zeroing it out means is that it becomes true. So, and the rest of it just works out. The details are not important, but the translation works. Okay. And this has nice properties. The translation has really nice properties. It maintains some invariance, and it allows us to basically prove what we are attempting to prove. And the proof is totally structural on the proof of the sequent we start off with. Okay, it's very uniform. It proceeds very, it's very structural, and so that's what we are. I don't need to show you the details. But let me just show you one or two consequences of this, okay? So in fact, just one, and then I will conclude. So let us say, okay, here is a really simple thing, which you already know is not true, but gives you an example of how we use the translation. So I want to show that I cannot derive box A P from P, okay? So what do? I go and apply my translation to it. So the translation of P is true, the translation of box AP is P. So what my theorem says is that if P implies, if I can deduce box AP from P, then I must be able to deduce P from true, but now in intuitionist propositional logic. And now I know that's not true, so this is how I deduce non-provability. Okay? And one can use this in a series, with a variety of examples. Okay? This gives you a sense for it. Just to conclude, so what I've shown you is a sort of a principal indexed version of intuitionist S4. I've tried to examine non-interference in this context. I've tried to build a logic with more proofs than necessary, just so that I can apply it to systems with fewer proofs. And just, I think, just in terms of future work, we believe that this theorem holds for a much, much larger context. I mean, we think it holds for a logic which includes disjunction, which is not that surprising. But we also think that it holds for things which include polymorphism, so second-order quantification. And we think it holds for type theories rather than logics. For example, where you have recursive types, right? And the reason is because non-interference is a property of proofs. So there's good evidence to suggest that, in fact, it holds for a richer system. Okay? And we are hoping to, the methods which I showed you right now are too syntactic to generalize to these things, but we think it's going to work in a bigger context. Okay, thank you.
Any questions?
Yeah.
Right?
Yeah.
So does that mean that proof, is it to somebody, but not necessarily to somebody else? Or is that somehow?
No, that's not how I was thinking about it. That's not how I was thinking about it. So
somehow
I say, so what I mean by that is, so if you look at think of a proof in a logic as a dynamic balance. Okay, so what do I mean by that? So if you look at a proof in a logic such as the one I have described, what we know is we can think of this proof. If you look at it through the lens of linear logic, you can think of such a proof as basically being somehow just built from a collection of axioms. Okay, that's really what it boils down to, and that's what I meant by a dynamic balance. And that property of proofs holds even for the richer systems, even though some of these things are not logic anymore. I mean, with recursive types, it's not logic in the sense we understand. And that's what I meant. That's why we think that it holds for the.
Where does the non-interference come into play? It's a property of proofs. Now, what does it mean here, non-interference?
That means that even though I have been trying to, I stated non-interference as I described it in terms of the formulas by saying, if I deduce something of box A, then I must not be using anything of box B. That's how I described it. But the reason it holds is because of the proofs of these formulas. So it's that's what I'm trying to say with it's an invariant maintained by the proofs of the system. Okay.
Any other questions? Okay, let us thank the speaker.